Hello, everyone. My name is Oleg Šelajev, and if you want to find me online, I mostly go by @Šelajev. You can find me on various socials and whatnot. So if you have questions about today's presentation or any of the topics there, you can just find me online, approach me. I'm very approachable. People say very easygoing, and I'd love to chat with you. Today's topic that I want to cover is productivity, sustainability, and fun in modern Java, which is, I think, a very, very important, a little bit philosophical take on where is Java heading, knowing where from Java is coming. It's very important to realize also where it's heading. So we're going to try to look at a few recent developments, as like in the last couple of years in the Java ecosystem. And we're going to try to look at them through the lens of whether this is a good thing that enables better productivity for developers. It enables Java ecosystem to be possible, to be excellent in the long run. That's what sustainability means. It means that we can do Java, we can create applications in Java in the long run, not just today, but like in the next 25 years. And also, we're going to look whether this is fun, whether this is something that makes developers happy, because that is I realize that this is like an essential part of sustainability, right? If developers are not happy, then I don't think anything can save the ecosystem. But it's also an additional thing, right? There are many examples where something is not fun, but we're still doing that because it's an industry standard and it's very hard to migrate off. Like, for example, Jira, right? My name is Oleg Šelajev. I work at Atomic Jar, which is a company made by the maintainers of the test containers libraries, which is the libraries for integration testing. I work as a developer advocate. You can check out both test containers and Atomic Jar web presence, and just thank you for them to support me coming here. So when I started preparing this presentation, I wanted to see what we think about Java right now. For many years, there were topics about how Java is dead, or Java is slow, or Java is verbose, or Java is all kinds of horrible. All those dramatic headlines, all those discussions, how there has to be something better. Unfortunately, Google failed me at that because it's a personalized search. So I don't think Google thought that I would be convinced that Java is dead. Instead, showing me helpful examples how to do certain things, which is very, very good. But I'm sure that you've heard and you also maybe participated that as either bystander or maybe an active voice in those discussions, whether Java is dead, whether we should migrate somewhere else, whether Java is appropriate for the cloud, whether Java is a good choice for new developers, whether there is enough new blood in the ecosystem. And when I say Java, I mostly mean all the JVM languages, because at the end of the time, this is it all runs on the Java virtual machine, and it all produces Java bytecode, and it's mostly Java. So there are like some syntactic differences, but it's all one big family, right? So Java is not dead, and today I want to make three claims. I would like to say that Java is modern, and I want to look at how modern Java is and where it's heading. I want to look at speed, at performance, and I want to make a claim that Java is fast, and I want to make a claim that Java is lightweight. So let's get right into it. Java is modern. Whether that is true or not, we need to understand the context of where we are now in Java development and the recent advancements and where it's all heading. That's how we can build a picture of what's coming in the next few years, and whether we can say that Java is a sustainable choice that will allow us to build successful business applications for the next years. So a few years ago, starting from Java 10, I think, the Java release cadence has sped up dramatically. To 2 releases a year, Currently, Oracle offers the long-term support maintenance for every fourth release. So Java 17, next one will be Java 21, and so on, with an overlap in the maintenance windows, so people can migrate nicely from one LTS version to the other. There are, of course, multiple vendors which can also offer different support strategies and maintenance modes. But in general, I think it's a very, very healthy ecosystem, and it is much, much easier now to migrate to the upcoming Java versions than it was before. And when I say before, I mean Java 8. I'm not even talking before Java 8 days. So before, those were the dark ages, and they were great at the time. And Java 8 was great at the time. But now we are, more than a decade later. Maybe it's time to move on. And the practice has shown that updating and keeping on track with the newest releases is much, much easier than before. So at the same time, I'm pretty confident that if I would ask you what versions of Java you are using in production on your most important and active projects, then most of the audience would tell me that they're either on Java 8 or 11. I suspect that currently Java 11 would win, which I think is a great development, but it's still lagging behind for quite a bit of time, right? But Java has sped up. There are multiple vendors. They're a very healthy ecosystem. There are also additional projects like GraalVM, which is very, very interesting. It builds on OpenJDK. It builds on the existing Java ecosystem, and it provides with additional features which might not exactly fit into the picture what OpenJDK, the reference implementation of Java, wants to be, but which are very, very interesting to the ecosystem. And there are a number of those, but I have good knowledge of GraalVM. I worked on the team for a couple of years. So I like the project and technology even still, while I'm not affiliated with the team. So I felt important to highlight that, even also because there is later a thing about GraalVM. So I think Java is moving forward at a very healthy speed. There are a multitude of options for you to either stay with the latest or greatest or not. So now, very quickly, just to show you how it changes in the last couple of years, I want to run through a couple of features a couple of features. Wait, come back. How do I? And I'm sure that you saw them sometimes, or you saw them eventually, or you will see them, or you know how it is because you're just following the development of Java. But still, I would like to highlight how they come together through the number of releases. So one small feature that I want to show you is the text blocks. This is, of course, not the most sophisticated one. It's just a multi-line string, hello, Devoxx Ukraine. We can just have a multi-line string here. What's important is that when Java eventually got this feature, and I think it was Java 14, I think it was 14 that managed that. What we got the ability to do this really, really well. It seems like a simple feature, right? You just have the multi-line string, but what's important is that, for example, it preserves indentation, and it allows you. It is much, much nicer implemented than some other choices in other languages, right? So it indents by this green line here on the left, and it's something that developers thought of, not just rushed into implementing this however they want, but they actually thought about this and implemented a nice version of this. So another nice addition on top of that, not on top of that, but like in general, which we should know, and which is one of the biggest things that you will see if you update from, like, say, 11 to 17. I'm currently running Java 17.01, built by Oracle, downloaded by SDKman, with preview features and everything here. One thing that you need to know is the existence of records. A record is a class which has a number of components which are represented by the names there and the types here. For example, I can have a simple person class. A record is a class, and its state of the class is represented by the components, only the components and all the components. Now, this class has a number of things generated for us. It is the record keyword here takes care of serialization, accessors, constructors, and everything else. So with just a simple one-line definition, I can then have a new class, which I can nicely use as this, like new person. And then I have my constructor. So we'll have Oleg and how old we are. We are 34. Oh, God. Yeah. We come to this. And then, of course, we can print this. And we can see that it will get a nice toString method. It's just such a nice quality addition. You can replace quite a bit of classes. Not for all use cases records are good. For example, records are not great when you want to have mutable objects, or you want to have object hierarchies, which records do not support. But they are very, very good in multiple contexts. So now Java is less verbose, and records play very nicely with all other features as well. So let's see what other features we have then. We have a number somewhere in, I don't remember which one. I think JDK maybe 12, maybe 12. We got the smart casts. So for example, if we have this person and we're gonna say that it's not a person, we're gonna say it's an object. Sometimes we have the objects. What we can do then, we can check if somebody is a person, is that the object is a person, and what we can do, we can also assign them to a variable. This way, here in this block, in the context of this block, person is immediately a person. So you can see I can have the accessors to the things, and the person is now has the type of a person, which is very, very good. Makes our code more readable. It eliminates the unnecessary clutter from the things, and it all of course works still the same way. It prints the accessor thing, it prints the thing. And this is the smart casting. This is the smart instance of operation with the additional cast. Now, this is one thing. On another hand, after that, somewhere in the next features of Java, we got the switch expressions. Maybe we got it at the same time, but here's this. So we have those smart casts. Then we got the switch expressions, which is the normal thing, right? So before switch was a statement, and now switch is an expression. We need a variable here. What do we need? Integer parse args 0. It's an expression. We can assign the result of the switch somewhere, and then we can have the number of things. For example, we do 3, 5, 7, 9, and we say this is odd. Can we do this? It's an arrow operator, right? And then default, we say even. It looks like a normal switch, but it is now an expression that we assign. We can use it anywhere. We can use an expression, and we can assign the results to things, which is much, much simpler and from the developer point of view. We also don't fall through that. So if we have 1, 3, 5, 7, then we get odd, and then we follow with the even. So now we have those two things, which is one of them is the expression of the switch, and the other is a smart casting of the parameters through operators. And what we can do now, we can do now the phenomenal thing, which is called the pattern matching for switch. And this is a little bit more involved. How do I do this? How do I do show? Let's create method, public void method, and we'll say an object. Why not object O? Now, this is where those two features come together, and this is where we can see how development of Java very nicely through they came in different releases, right? They came through the time, but they were delivered in pieces every 6 months, and it nicely shapes the future of the language altogether, right? So pattern matching, let's say, what we need to do. Let's return switch, and then we do switch on the object, and here we can have the different cases. So for example, if we pass, say, an integer, we can cast it, and we can, with the arrow, say that we want to return return 1 plus, I don't know what we want to return. I just want to show the syntax. So of course it's an expression, and then case, for example, let's say double b. We do the same, but we don't say double, so it's not the same. And of course, this is an expression. This is a switch. We need to take care of the default branch, so we say default and return object. So this is a very, but not. What doesn't compute here? String. Okay, very good. It's an expression, so we need semicolon. Very, very nice, right? So now we have a method where we can implement the switch on the type classes here, on the classes, which allows us to create very interesting code, which much easier. State machines, any message passing, anywhere where we need to determine the logic based on the class of the object. This is very, very handy. And now the next one is even better. The next one feature is called the sealed classes, right? So this is where it becomes very unlike Java 8. So if I have the class, for example, sealed class, before I could only make it either not public, of course. I could only make it either final and deny all inheritance, or non-final, and then anyone can inherit from it. So now what I can do is I can call it a sealed class, and I can permit certain classes implemented. So let's say we can have a sealed class, and we can have inner class here, right? And we can have A, and we must also verify, say, whether this is, why this is not working. Okay. So we have two classes. We have a class hierarchy: sealed class A, sealed class B. And now nothing else can extend from sealed class, because it only permits the extension and inheritance by A and B, which means that you can have the class hierarchies in your code where you use the class hierarchy normally, but no one else can extend it. And that means that in our case here, what we can have sealed class A, and let's do private, and we can have the sealed class B, and we can be certainly sure, that this is B, right? That our hierarchy is solid. And in case we want an extensive thing, we can just say that if it is a sealed class, then say that this is a sealed class. And now we can see that in this switch, we don't have the default branch, and we extensively list the whole hierarchy that we can do. And why is that possible? Because the class is sealed, and there is no way we can extend this hierarchy, or we can break this switch, which is a very, very interesting combination of the previous things that we had, the expressions and the smart case casting, and also the sealed classes. And it all works together very, very nicely. You can see here that, for example, if this is not, say this is an interface, it can be an interface, and then this could be a record. And of course, it needs to implement things, right? Because it's an interface now. And it all works together. So someone, well, and by someone I mean people who developed this, thought about this whole thing and how all those features come together and delivered them very nicely through the course of releases. So now even more things are coming forward. There is now even a JEP for Project Loom for implementing virtual threads. In Java 17, there are some advancements with the Project Panama, giving you better access to native functions through the common foreign function interface. All those are very interesting. Some of them are available as the early access builds. I don't think Project Valhalla, implementing value types, inline types, value class. I don't remember what's the current name for that, but implementing a different, more neat packaged memory layout for primitive classes and for normal classes is very far ahead. But those other things are somewhere in the horizon. So what I wanted to say is Java is moving forward. Java is moving forward now in smaller steps, but it is looking very, very different from previous Javas that you have. If you look at this part, and if all you saw before was Java 8, then it doesn't look anything like Java that you know. Even if you look at the switch here, it is a much more modern, functional language where you can do many things easier than previously. So I would claim, so here, let's just skip all the slides there. I would claim that all those things nicely show that Java is moving forward in a very nice, even in a very nice fashion. So let's talk about performance. And here I would like not just talk about the JVM and the advancements in the internal Java infrastructure. Of course, there are advancements in the compiler. There are new GCs available. Now, if you're running 17, probably you get the best G1 GC that you can get out of all Javas. You get the ZGC, you get the best Shenandoah, and all others. But I also want to talk about fast in the typical context where people say Java is not fast, which is the modern cloud deployments where we want to auto-scale things to zero and pack our applications into memory very neatly. So I want to talk about the cloud. And to do that, I would like to talk about Micronaut, which is a modern framework for building applications. It's an application framework. And one important thing, what sets Micronaut apart and which was the part of their core mission and core vision for how Micronaut should be from the very beginning, is the pre-computation of the configuration and everything that is possible to pre-compute before we start running our application. So that includes the proxies, all the bin introspection, metadata of the annotations and annotation processing, computing the dependency graphs and injecting configuration. All that is done using annotation processors, using the normal default features of Java language. And from the very beginning, that was a big part of the Micronaut value proposition and the idea how it could improve on the existing solutions. That was a couple of years ago, and that is a pretty great result. Now, after that, after a little bit of time, GraalVM project was announced, and a part of that was the GraalVM native image capability, which allows you to take your application and compile it ahead of time into the native binary. And it does that by building on this idea that when we have our application and we build it and we give it to the whoever runs our application, either ops team or Kubernetes or our container runtime, we give something immutable. We give something that doesn't change after the fact. So we don't need a lot of dynamism on top of that. So what we can do, we can pre-compute everything. We can compile things ahead of time, and they will be nice and ready for when we need them. So GraalVM works really, really well with Micronaut, and Micronaut's approach works really, really well with GraalVM, specifically with native image. Why? Because native image works on the Java bytecode, and Micronaut does all this pre-computation using the annotation processors, which is an essential phase run during compilation of your Java source code into the classes, right? So when you run Java C, there is a certain time where it looks at the annotation processors, whether any of them are available, and then runs them. And then after that, so we can think about that as a separate phase. And then after that, we can run any bytecode manipulation that we want, including compiling native image. So separate phases, that works very elegantly together. Now, what it gives us great startup because everything is pre-compiled. It gives us a lower memory footprint because we can both remove the unnecessary components from our application, but also we don't have to spend precious resource budgets on things like JIT or things like holding the class metadata in memory, because we compiled everything. We don't need that. It also gives us neat small packaging for the same reasons, because we did a bunch of things at the beginning during the build time, and it just all works. Now, GraalVM, of course, moves forward. It moves forward even with the faster cadence than OpenJDK, having 4 releases a year, and you can get that nicely from their websites on anything. What it does, a part of that, is the native image build that takes your bytecode, runs the static analysis, compiles the thing, works really well. Now, currently, this was for quite a bit of time. This was a problem with various frameworks and various applications, both in terms of compatibility with the existing code bases and the preference for some frameworks to run very dynamic features, making decisions at runtime specifically, which complicates this central part of the points to analysis, which is a static analysis. It just looks at the code. So if you do things at runtime, it cannot always see through them. That was a little bit of a problem. But I think by today, if we look at today's landscape, this is a problem that is, even if we cannot say that is sort of solved, it is a problem really on its way to being solved. Most frameworks work with that. Most libraries work with that. The default expectation when you run native image is that it will nicely, if you follow all the correct steps, that it will nicely produce you a binary, unless there are some corner cases, which I am sure the teams will figure out. Right. So we built native image. We need to configure the dynamic parts, which you can do with the Java agent. You run the Java agent with your Java code. It runs, it records everything that needs to be configured, and feeds that configuration to native image build process. And then you resolve this point of tension where the analysis is static, so it cannot see through dynamic things, because the dynamic things you configure using the tracing agent, which is very nice, very simple. It currently, I would say that it just works. The build takes quite a bit of time, which is not very pleasant. But then after a while, it produces the binary. And then the performance of that binary is really, really good out of the box. Really, really good out of the box. So if you look at that, this is the peak performance. Let me show you a quick example. So we have time, we have a little bit of time. I want to show you a very quick example of a Micronaut application here. So I'm going to go, and in a true futuristic fashion, I'm gonna open a code space, which is an online IDE on GitHub. I would run a virtual machine, and someone, meaning GitHub, will run a virtual machine for me, and it will give me the resources. Pick of resources, if I might ask. You can pick how much resources you want. Wait, but in general, so this is the powerful machine. Of course, it has the gigabytes of things here. It also loads my application from the repository. It's a very nice way of developing, or at least looking at some applications. So this is my Micronaut application, which is very simple. It has one controller. It's a web application. It registers primes, and it's gonna return me the prime numbers here. So we do this in the most sort of simplistic fashion. We receive a parameter, we pick two random numbers, and we find all the primes between the numbers by doing the following computation. We have the range for with mix and min and max. We stream all the numbers, we filter, we box, and we collect things. And when we try whether something is prime or not, we also stream all the numbers from 2 to the middle part and match all of the things. And then if all of them match that it's not divisible, that the remainder is not 0, then it's a prime. So a very inefficient, but a nicely showing thing how it works, right? So what I can do with this application now, I can go to the primes, and I can, of course, build it with Gradle, and I can also say Gradle native image. Micronaut uses the GraalVM's build tool plugins, both for Gradle and I think Maven configuration. By default, Micronaut uses Gradle. So what it can do now, it will just build my application. It will. I want to show you how to clean. I want you to show how it works. And also, it will take a moment to compile that application, as I said. So I want to show you both the trade-off there and talk about what is happening. So now my application will compile, of course. And this is like the whole Micronaut ecosystem will probably compile. The whole Quarkus ecosystem will probably compile. Helidon ecosystem will probably compile. Spring ecosystem with Spring Native is currently in experimental, but there were recently was a session at Spring 1 in September where Sebastian Deluze was talking about at which stage Spring Native project is. And it is in a stage where the team is certain that the approach that they took is appropriate and valid, and it's functionally, it works. So now the team there is working on improving performance. So performance and the coverage of the ecosystem. So more projects in Spring ecosystem work with Spring Native out of the box. So currently, of course, you can do Spring Security and JPA and Spring Data and Spring Validation and a number of projects, and the number of that it grows faster every day. But also, just think about it. If the team is working on performance, that means that it's functional, it is working. So when it will exit beta, I don't know, but it's currently in a really good shape. So now I can run my application here, which is very neatly. It will tell me that the ports are open. I can actually open that in the browser. Why not? Just show you. Look, it connects to my virtual machine instance. We need to do primes, random, and say something, and we can see that it gives us back prime numbers. You can check whether there's all primes, but I don't think there are any mistakes. This is actually a very cool part and the part of the current Java development. Of course, you can do things normally as you do with your IDE and everything, but you can also very, very easily get the throwaway ephemeral development environment in the cloud with just a couple of clicks. You can use that for looking at pull requests. You can use that for building certain things or experimenting with some quick changes to the things. and it works really, really nice. You can see here, so my application is super fast, super fast, super fast. This is 30 milliseconds. This is a very, very, very simple, very nice measurement. I want to show you a tweet, which I didn't want to show you before. Mark Sales. Mark Sales is a person working at Amazon at AWS, and just recently he was showing, and his colleague Nicholas was showing the numbers for AWS Lambda with the warm and cold start performance in Lambda, asking people what language they think that is. Right, and the results are like this. So for the cold start, when it's a cold start on Lambda, and this is the Lambda with 256 megabytes of RAM. The cold start is under a second, half a second, most of the time, 800 milliseconds together. And then when it's not cold start, the latency of returning something, and this is a sample application that writes and reads something from the database, from Dynamo or something, some Amazon database, right? The latency there for the request processing is literally in milliseconds. Yes, sometimes it like sits behind the garbage collection or something, so the maximum latency is still under a second, but normal latencies are for the serverless computation is very, very good. And mind you, this is so if we look at this here, this is the GraalVM running at 256 megabytes of RAM. And people in the comments there very often were saying that this is Rust. Of course, Rust will have a better cold start performance here. So this is not the most sophisticated guess, but this shows that the numbers that Java produces there are very, very, like on the first glance, if you don't actually think about them very long, they're sort of like other languages, which are clearly much, much better suited for those fast-paced cloud deployments context. So I would claim that Java is fast. Java is very fast when we know it, when it runs during long periods of time, when everything warms up and all good. But also Java is fast in the context where Java is typically not thought to be fast. And this is the recent results on the peak performance of GraalVM native image. And you can see there that while the community edition native image is lagging a little bit behind OpenJDK, if you use a more sophisticated compiler, if you use the profile guided optimizations, and if you use G1 garbage collector, then the performance, this is a peak performance on normal Java industry standard benchmarks, Renaissance, Da Capo, Scala bench seeds on the JDK11, right? So those are not just sample hello world application. This is a solid benchmark suits, a solid experiment, right? And here is a very, very interesting thought for you. If you use, yes, GraalVM Enterprise is a product, yes, it requires certain licensing and so on. You can use this for free in some context. You have to purchase it for other contexts. But just from the technology point of view here, I think this is pretty spectacular that compiled ahead of time without knowing the actual, having a profile, but without knowing the actual data at runtime, native image can achieve almost the same throughput as OpenJDK. And I think this is very, very spectacular, because it still will have instant start. It still can have, of course, I'm sure for the similar performance throughput at max, it needs to have a similar memory consumption. So I'm sure the experiment here was solid, but it can run with lower memory consumption if you wish to. And it's pretty spectacular that those two bars in the middle are almost the same. So Java is very, very fast, both in native image mode and as a JIT. And there are a number of things that use native image. There is support in the libraries. Some people rewrote some of the Kubernetes plugins from Go to native image because they get the same performance, and they're also much happier with the result because they are using the language that they know and love. This particular example is about Scala, which also works with native image, but it's also, yeah, it's a very great anecdotal data point here. So, and the last point I want to make is that Java is lightweight, and I want to make it on the example of another framework which I like very much, which is Quarkus. And Quarkus is another new application framework which for a long time positioned itself as the lightweightest, lightest, and fastest, was a little bit cheeky marketing phrase, supersonic subatomic Java. I'm not judging, not judging. Personally, I feel it's a little bit cheesy, but to everyone, theirs. So what Quarkus does is it works, of course, very well with native image, and it can produce also those native image binaries that are super fast at runtime, at startup, and use very little memory. But another thing that Quarkus does, it tries to optimize for how nice it is to use Quarkus. So, and that shows in a number of things. It shows in how the configuration across the whole Quarkus universe goes, how there are some developer-oriented features like live reload that is built in the frameworks, and it's not like accidental. It's not something that someone created on the side and then like it works or doesn't work here or there, right? It is something that the team cares very much about, and this is something that they want to preserve through the new releases. So if you haven't looked at Quarkus, I would encourage you to just at least following the project and thinking about particularly that part, how the team tries to optimize for the developer experience. So let me show you here. One example there is we know that you can run integration tests using test containers. Test containers is a library that allows you to manage lifecycle and the creation of the throwaway ephemeral instances of the real software, like databases, so Kafka or Elasticsearch or cloud services like Local Stack or Google Cloud in Docker. And then in the integration test, you can run your application and you can configure it to use those services. So your integration test can be very nice. And with the very simple code, you can actually test your application in the proper environment against real software instead of mocking that or using like in-memory databases or spinning up Kafka in a managed cloud somewhere manually or with Docker Compose. So integration test story is very simple, very nice. Test containers provide a beautiful experience. Now you run the test the same way. You use your Java code, or in this example, this is Groovy. You run it. Tests are in the Docker container there. You can also put your application in a Docker, and it still will work all nice. But what Quarkus does, it takes this experience and enables that for the local environment. So, and let me show you this an example of a different thing. We have just a couple of minutes, and I would love you to show you. I will pick a different code space here. And because I want to show you how lightweight this is, I will pick a different one. I'll pick with 4 cores and less memory. So a smaller one. Unfortunately, the smallest one that code spaces offer you has 2 threads and 4 gigabytes of RAM, which, while sounds decent, my phone has more. I'm not sure if my watch has more than that. This is an old watch, so my watch probably doesn't have more than that. But if you have a modern watch, you probably have a very decent result there. So here's the thing. Here's my Quarkus application that will do the following thing. It will compute my prime numbers the same way. But what it also will, it will use a certain channel and it will send the results of the computation, how much time it took, into the channel, into Kafka. right? So it will, when the computation takes some time, it just takes the start and the start again, and it computes how long does it take to compute numbers between min and max. Because this prime numbers calculation is kind of horrible, awfully inefficient. So we want to see how much time it takes to compute that using two streams, like n squared streams, because for every integer in this stream, we also need to create another stream and match all things. So n squared streams, which sound like something that can take quite a bit of time. So let's do this. So here's my HTOP, just so you see 8 gigabytes of RAM, 4 threads, all good. A tiny application. This is what I do. I'm going to run this. How do I run this? I run primes Kafka, temporary primes Kafka, and I will do Maven Quarkus def. And this is where quite a bit of magic happens. Now it will run as normal. It's not the fastest, but it's also not that bad. It will run and it will figure out that I want my application to use Kafka. And I configure Kafka that I want to use Kafka, but I don't configure where that Kafka actually is. So what Quarkus does, being a nice framework that cares about developer productivity and developer well-being, it has integration with test containers to figure out, oh, there is no Kafka. I'm going to create one Kafka for you using test containers, and I'm going to run it, and you're going to have that Kafka ready. So you can see now, let me see the ports, 8080, open the browser. You can see now that if I have my application here. If I do primes and I do some number, we can see that this Quarkus application responds to us. We can also see that there is actually Kafka ready. So it's the same thing. Wait, it's the same thing, but it's a development console. The development console doesn't work. I don't know why. We'll see the Kafka. If we want to check where the Kafka is working actually or not, I have another application here, right? And this is where it takes everything to the next level. So we have primes Kafka listener. And I have a few moments. I'm going to run it immediately. So what it does, this application does, it connects to the Kafka, and it also doesn't configure any Kafka. It doesn't configure any Kafka. So it just says, I want to run on a different port if I want, and I want to use Kafka, and it doesn't say where the Kafka is. Because in production, that would be external configuration for me. So it just wants to consume the messages, right? And now this is the cool part. Quarkus with the dev services is using test containers nicely in a way that when it determines that there is already applications running, for example, Kafka, because Kafka individually is not that interesting, because you throw messages in, how do you get them out? You don't. So Quarkus notices that I have two applications running and requiring Kafka, and it connects them to the same instance of the test containers, which is an incredible thing to hear. You can see that I get the computation logs on this listener thing. So you can use that. We recently announced an addition to test containers is a service by Atomic Jar called Test Containers Cloud. You're welcome to look at that. This is where you don't have to have local Docker installed, but the containers that you want to run are running in the managed cloud in a serverless fashion. So you just can run your tests without actually Docker being there. So you can see here, for example, in my thing here, if I do Docker PS, there is only the workspace, the workspace Docker itself, which is just my container here, and there is no Kafka running around. So Kafka runs in the cloud, making my experience much more lightweight. So I would claim that our application, our Java ecosystem is now fast, it is modern, and it is very lightweight. Of course, there are some conditions, and sometimes you have to pick two or out of three, but it is possible. And developing applications in Java currently is very, very enjoyable, which I think is a very, very good situation, and it's a very good step forward. And I think the future is bright. Thank you very much. I think we're out of time. I am not sure if I'm still connected to the thing. I hope you actually heard everything of that. And thank you very much. If you have any questions, find me online.
Oleg, you're still connected. You're live, and thank you for the talk.